Hello friends, this is one more application of greedy method. This is single source shortest path algorithm. As per the greedy strategy, we will start from node number 1 and we will try to identify the shortest path in this particular graph. If you are observing, there are 6 nodes in this graph and there are multiple edges among them. This is unidirectional graph. What we have to do, we have to start from node number 1 and we have to identify distance between one and each and every other node, and that should be the shortest one. So let us see how exactly this algorithm proceeds. For solving this particular example, we are going to make use of adjacency matrix, because whenever we are going to write the code, at that time we will have to provide adjacency matrix to the machine. Now you can see in the section below there is a matrix, or there is a two-dimensional array which has been indicated here, which has been shown here. In the row there is edge number 1, and in the column all the other nodes are there. So there are 6 nodes. So start from 1, 2, 3, 4, 5 and 6. If you are observing, 1 to 2 distance is 7, so it has been marked here. 1 to 3 there is no direct edge, that's why it is infinity. 1 to 4 there is no direct edge, that's why it is infinity. 1 to 5 similar. 1 to 6 it is 3. Now we will start from this particular column and we will proceed. This is a feasible solution. All of us are familiar with the feasible solution and optimal solution in greedy method. What exactly feasible solution is? It is the current solution which you are having. But if you are finding some solution which is more optimal than the feasible solution, that solution becomes the feasible one, and we'll consider that as an optimal solution. So here at the beginning, 7 is the smallest one. 7 will be compared with infinity. Infinity is bigger, 7 is optimal. 7 will be compared with this infinity, 7 is optimal. 7 will be compared with this infinity, 7 is optimal. But when 7 will be compared with 3, as 3 is smaller than 7 and it is more optimal, then here optimal solution will be changed. So in the first step, the optimal solution is 3, and the edge which is represented by 3, the node which is represented by 3, that is node number 6. So what we are going to do in this particular step, this is the current optimal solution. So we will consider that and we'll go to the next step. If you're observing in the next step, 1 and 6 are considered. Now we will have to identify, starting from 1 via 6, is there any other path which is optimal than this 7? I'll repeat this. The current distance between 1 and 2 is 7. Now, as we have got the shortest distance between 1 and 6, we have marked it as 1 and 6. Now, I have to identify by making use of 1 and 6 both whether I can find any other shortest path. Now, if you are observing, can you find any optimal distance between 1 and 2 via 6 which is less than 7? So 1 and 2 is here, the current distance is 7, but if you are observing via 6, 3 plus 2, that is 5. So as 5 is more optimal than 7, then we have replaced this 5 with this 7, as this is the optimal solution. Is there any distance between 1 and 3 which is more optimal than infinity? That we will write here. So if you are observing, from 1 via 6 to 3, is there any distance which is more optimal than infinity? From 1 via 6 to 3, if you are observing, 3 plus 5, that is 8, and 8 is more optimal than infinity. That's why infinity has been replaced with 8. Same is the scenario in the next column. From 1 to 4 via 6, Is there any distance which is more optimal than infinity? If you are taking into consideration the graph from 1 to 4 via 6, there is no direct edge. That's why we are repeating this infinity here. There is one more node, that is 5. From 1 via 6, is there any other distance which is more optimal than infinity? The current distance is infinity. So if you are observing from 1 to 5, the current distance is infinity. But if you are going via 6, this 3 plus this 6, that will become 9. And 9 is more optimal as compared to infinity. That's why as per the greedy approach, this 9 has been replaced with infinity. If you are observing node number 6, that has already been encircled, because in the previous step that was the most optimal solution. That's why we will repeat that as it is. So in the second step, if you are observing, we have got two replacements for infinity. One is 8 and one is 9. This is possible because of node number 6. Now, as 3 is the current optimal, we have to identify in step number 2 who is the immediate successor of 3. So immediate successor of 3 is 5. That means the least element which is greater than 3, that is 5. 8 and 9 are bigger than 5. So 5 is more closer to 3. That's why we have encircled this 5, and 5 is representing node number 2. That's why in the next step we are considering node number 2. So in the next step we have added 1, 6 and 2. So we'll write this 5 as it is here, and we will focus on node number 3. From node number 1 to node number 3, is there any other distance via 6 and 2 which is more optimal than this 8? So we'll go in the graph from 1 to 3 via 6 or 2. Is there any distance which is more optimal than 8? The current optimal distance is 3 plus 5, that is 8. So if you are observing 3 plus 2 plus 4, this will become 9. 7 plus 4, this will become 11. So right now there is no distance which is more optimal than 8. That's why what we will do, we will continue with the same distance, that is 8. Now if you are observing, we will go to the next node, that is node number 4. From node number 1 to node number 4, is there any optimal distance which is less than this infinity, which is optimal than this infinity? And what we will consider, we'll consider these two nodes via 6 and 2, 6 or 2. So from 1 to 4 via 6 or 2, is there anything which is more optimal than infinity? From 1 to 4 via 6 or 2, if you are observing, neither 6 nor 2 has direct edge to 4. So what will happen, we'll continue with this infinity. Now come to the next node, that is 5. From 1 to node number 5, what is the current distance? Current distance is 9. From node number 1 to node number 5, is there any other optimal distance than 9? We'll go to this particular graph from 1 to 5 via 6 or 2. Is there anything optimal than 9? If you are observing, 7 plus 2, that is 9 plus 6, 15. That is not optimal. Again, 3 plus 6, that is 9. That is the current optimal solution. So there is no one who is more optimal than this 9. That's why we'll copy this 9 as it is here. And 3 has already been taken as an optimal solution. So if you are observing, this 3 is repeated in every column. This 5 is getting repeated in every column. Now we have got all the feasible solutions in this particular row. Now we have to find out the current optimal solution. What was the previous optimal solution? That was 5. Who is the immediate successor of 5 in this particular row? That is 8. So 3 has been considered, 5 has been considered. That's why 8 is the current optimal solution, and 8 is representing node number 3. That's why in the next row, we'll consider 1, 6, 2, and 3 as the current optimal solutions. Now again, we'll have to repeat the same procedure. So from node number 1 to node number 2, it is already identified as an optimal. From 1 to 3, it is already identified as an optimal. That's why we'll copy this 8 here. From 1 to node number 4, the current distance is infinity. Now we have to identify from 1 via 6 or 2 or 3, Is there any optimal distance than this infinity? Let us see. From 1 to 4 via 6, 2 or 3. So if you are observing, we are getting here 7 plus 4, that is 11, plus 8, that is 19. If you are observing here 3 plus 2, that is 5, plus 4, 9, plus 8, 17. But if you are observing here 3 plus 5, that is 8, plus 8, that is 16. So in the current instance, you can find 16 is the optimal solution. So can we consider that? Yes, we can consider that. So 16 will be considered via the current path, that is 1 to 6, 6 to 3 and 3 to 4. That is the optimal solution. So 3 plus 5, 8 plus 8, that is 16. Is there any other optimal distance than 16? So let us see. 6, 2 and 3. There is no optimal solution than this 16. That's why we will have to replace this infinity with this 16. Now go to the next column. If you are observing node number 5, the current optimal distance is what? 9. Is there any distance between 1 and 5 via 6, 2 and 3 which is more optimal than this 9? Let us see. 1 and 5 via 6 or 2 or 3. If you are observing, there is no distance which is more optimal than 9. That's why this 9 has been repeated as it is here. Again, in the next step, node number 6 has already been optimized as 3. So if you are observing, all the entries are fulfilled in this row. What was the optimal solution in the previous row? That was 8. So who is the immediate successor of 8? That is 9. So here 9 has been encircled. The node which is represented by 9, that is 5. So in the next step, we will include 5 also. 1, 6, 2, 3, 5. So 5 has been included. Now which node is remaining? All of the nodes, if you are observing, we have got the distance. But we will have to again check whether we are getting some more optimization or not. So 1 to 2, 5 is optimized. 1 to 3, 8 is optimized. 1 to 4, the current distance is 16. Is there any other distance via 6 or 2 or 3 or 5 which is more optimal than the 16? Let us see. We are having these 4 nodes right now. 6, 2, 3 and 5. 6, 2, 3 and 5. If you are observing, the current path is 3 plus 5, 8 plus 8, 16. But if you are observing on the other hand, 3 plus 6, 9 plus 3, 12. So 12 is more optimal than 16. That's why here 12 is replaced with 16. If you are observing carefully, there is no other distance which is optimal than 12. So we'll replace this 12. Again, 9 has already been optimized and 3 has already been optimized. So if you are observing, starting from 1 to each and every other node, we have identified the optimal distance. This is how single source shortest path works. This is the application of greedy method. Thank you.